Hello, dear students. We have been studying the various problems related to the deposition of elements or Faraday's law. In that context, we need to find out the amount of charges in Coulomb required to convert 1 mole of FeO to 1 mole of Fe2O3. Here, if we really calculate the oxidation state of Fe, for FeO, we find oxidation state of Fe is plus 2. For Fe2O3, the oxidation state of Fe that we find is plus 3. So in Fe2O3, Fe is plus 3. In FeO, Fe is plus 2. Thus, when actually FeO is converted to Fe2O3, thus when FeO is converted to Fe2O3, actually Fe plus 2 is converted to Fe plus 3 and 1 electron is removed. This is how we can understand. So when we write it into the words, what we write, 1 FeO turns into Fe2O3, actually 1 Fe plus 2 ion is turned into 1 Fe plus 3 ion, which requires 1 electron. So 1 FeO oxidized to Fe2O3 need 1 electron. That means 1 mole of FeO to 1 mole of Fe2O3 need 1 Faraday charges. 1 Faraday charges means 1 multiplied by 96487 coulomb, that is 96487 coulomb charges are needed. My dear students, sometime instead of 96487 coulomb, 96500 coulomb is also taken as the Faraday constant. This is more exact. 96500 is lump sum or approximate value, or it's a round figure. We should look at the instruction given into the question, and according to that we should solve the question. If a current of 0.5 ampere flows through a metallic wire for 2 hours, then how many electrons would flow through the wire? We are given what is the data given to us? The ampere of current that is passed, that is your I, is equal to 0.5 ampere. Your T is equal to 2 hours. 2 hours means 2 multiplied by 60 multiplied by 60 seconds. So to calculate number of electrons that flow, that is what we need to calculate. Now we find the answer. So we write Q is equal to IT. We put the value of I is equal to 0.5 and T is 2 multiplied by 60 multiplied by 60. That simply gives us the 3600 coulomb. Now we know that 1 mole of electron, that is 6.022 into 10 to the power 23 coulomb, 23 electron, and uh, that is what the charges, if we really look at, is this multiplied by the charge present on 1 electron, that is 1.6 into 10 to the power minus 9 coulomb, and that gives us the 96487 coulomb. So 96487 coulomb is equal to 6.022 into 10 to the power 23 electrons. The charge is, so 96487 coulomb charges have is there with this much of electron, and therefore if we have 3600 coulomb charges, what is the number of electrons we can have? And then by doing this calculation, we can simply write the number of electron would be 3600 divided by 96487 coulomb. For easy calculation, here you can write 96500 multiplied by 6.022 into 10 to the power 23. My dear students, this final answer I am leaving on you. So please find the answer and write it in your notebook on your own. Now we look at the next question. A solution of CuSO4 is electrolyzed for 10 minutes with a current of 1.5 ampere. What is the mass of copper deposited at cathode? Let us solve this problem. First, let us see what data is given. The data given is T is equal to 10 minutes, that is 10 into 60 seconds. Your current A is given 1.5 ampere. Then you have CuSO4 aqueous, which is generally having Cu plus 2 aqueous and SO4 minus 2 aqueous. This Cu plus 2 at cathode is converted to Cu solid. So one ion of Cu requires 2 electron and 63.5 U. Now, my dear students, there are also various kinds of, various numbers given as a molar mass for copper. It is better if it is given into the question itself, or else we can use the various numbers. So here I have taken the number as 63.5 for copper. So if we take 1 mole of Cu plus 2 ion, then we need 2 Faraday charges, and we will get 63.5 gram of copper deposited. Now we know that we have certain values of I and T given. So by putting the value of I and T, we find that 900 coulomb charges are being produced here. And so for 2 Faraday, that is 2 into 96500 coulomb, we get 63.5, or let us say here I have changed my idea and I have turned it into the 63. The value I have changed and I have taken it as a 63. So we get 63 gram of copper. So for 900 coulomb, we will get 900 divided by 2 Faraday multiplied by 63, and finally we will get 0.2938 gram of copper will be deposited. So this is how we really understand this question. Now we'll move to the next question. Let us read the question. A solution of NiNO3 twice is electrolyzed between platinum electrode using a current of 5 ampere for 20 minutes. What mass of nickel is deposited at cathode? So here the current is 5 ampere and T is 20 minutes. So here nickel is got plus 2, so it requires 2 electron to turn into nickel solid. That means 2 Faraday will give you 58.5 gram of nickel. The total charges what we get is 5 ampere for 20 minutes, that is 20 into 60 seconds, and finally we get 6000 coulomb. So 2 Faraday charges will give us 58.5 gram of nickel. Therefore 6000 coulomb charges will give us 6000 multiplied by 58.5 divided by 2 Faraday, and finally we get 2.73 gram of nickel that will be produced. Now we have the nice question, or three electrolytic cell ABC containing the solution of respectively ZnSO4, AgNO3 and COSO4 are connected in series. A steady current of 1.5 ampere was the passed through them until 1.45 gram of silver is deposited at cathode of cell B, because B is made up of your silver nitrate. How long did the current flow? We need to calculate what is the time for which this current has been flowed, and what mass of your copper and zinc were deposited. So let us try to solve this question. First of all, we should know that in cell B we have AgNO3 solution, and therefore AgNO3 that gives Ag plus 3 and NO3 minus. So at cathode of cell B, Ag plus will be converted to Ag solid, and if we take 1 mole of Ag plus, then we will use 1 Faraday charges and we will get 108 gram of silver. So we can simply say for 108 gram of silver we need to use 1 Faraday charges. So for 1.40 gram of silver we need 1.40 gram multiplied by 1 Faraday divided by 108 gram, and finally we get 1295.6 coulomb charges. So to deposit 1.45 gram of silver we need 1295.6 coulomb charges. Now we know that here current is 1.5 ampere. We do not know what is the time till which this current has been passed, and the total charges we passed is 1295.6 coulomb. And therefore using this, Q is equal to IT, therefore T is equal to Q by I. We just put the value of Q as 129.6 divided by 1.5, and we come to know that 863 second is the time for which this current has been passed through both the cells. Now through all the three cells actually. So now we need to go for the both the cell and we need to find out. See, Zn-SO4 will give you Zn plus 2 in cell A. So Zn plus 2 will give 2 electron and will get the Zn plus 2 get 2 electron and will get zinc solid. So 2 Faraday charges will give you 65 gram of zinc. Therefore 1295.6 coulomb charges will give us how much copper and sorry how much zinc, and we'll find that 0.438 gram of zinc is produced. Same way, if we look at the cell C, then in cell C we have copper sulfate that gives us Cu plus 2 and SO4 minus 2, and Cu plus 2 will take 2 electron to give you Cu. That means for 2 Faraday we will get 63.5 gram of copper, and therefore if we pass 1295.6 coulomb of charges, the mass of copper produced is 1295.6 multiplied by the molar mass of copper divided by 2 in 2 Faraday, and finally we get 0.426 gram of copper is deposited. Thank you, my dear students. Happy learning.